a classic first sort of Newton's second law problem, which is done, is the elevator problem. I imagine that I have an elevator of mass capital M, and it's attached to a vertical cable. And I'm an engineer, and I want to design this elevator so that it can carry a total load of capital M without breaking the cable for a particular acceleration. Before we do this problem, I want to review a little bit from kinematics earlier in the semester. In particular, it's kind of important that we understand what positive and negative acceleration are in a one-dimensional problem. So I have chosen, as is usual, the positive y direction to be vertically up. Now, if I am moving up, if I am moving in the positive y direction, if the elevator is speeding up, then it has a positive acceleration. If the elevator is slowing down and moving up, it has a negative acceleration. So a sub y will be negative if it's slowing down, or positive if it's speeding up. If it's going down, moving in the negative y direction, then if it's speeding up, its acceleration is negative, and if it's slowing down, its acceleration is positive. So I want you all to remember that you can't tell whether something is speeding up or slowing down just by the sign of the acceleration. It depends on how it's moving in your coordinate system. So you all might want to just pause the video for a minute, sort of review and make sure you understand these accelerations. Okay, so let's do this problem. Choose a body. Well, we're going to just choose M as the body. What are all the forces on M? There's its own weight, which is mg down. Oh, hang on, hang on. Catch up here. There we go. Okay, so there's its own weight mg down. There's some tension T in the cable up like this. And I've chosen a positive y direction pointing up. Resolve all the forces. They already are, because this is a one-dimensional problem. Apply Newton's second law. The sum of the forces in the y direction is equal to 0, is equal to T minus mg, and that's equal to the mass of the object, which is m, times a. And so that tells me that the tension in the cable will be equal to m times g plus a. So what this means is, if you are accelerating up, for example, then the acceleration will be positive, and so you have to be able to have a cable which is stronger than that cable, which is the minimum necessary to support this much mass. Okay? Very simple problem. You also see that if you're going up and slowing down, then the tension in the cable will be less than the weight. You remember back when I was doing some of the Newton's first law problems, I said that you are going to see problems like this. when we get to Newton's second law, and that you should not get in the habit of thinking that the tension in the cable is equal to the weight that's hanging from it. That's certainly not the case if there's an acceleration. Okay, now I always like to do this problem in a little more detail because this will emphasize some of the features that students get wrong sometimes. Okay, so what I'm going to do is I'm going to imagine now we have an elevator. The mass of the elevator is capital M, and we have you standing in the elevator. The mass of you is little m. And I want to study this problem in some detail and see what I can learn. Now let me simply first of all point out that we sort of know the answer here, because if we choose the body as everything, m plus m, okay, then there'll be a tension T and there'll be a weight m plus m g, like this. And you see this is exactly the same problem I just solved. Okay, so I can tell in this particular situation that if the acceleration is a, then the tension has got to be m plus m times g plus a. So in essence, I already know the answer. But as I said, what I really want to do is I want to individually look at U and at the mass. Okay? So this is just a reminder that we've sort of already done this problem with m plus m being the mass of the elevator and its load. I'm going to erase this stuff here now so that I can sort of start with a clean slate here. Whoops. Guess I shouldn't have erased you. Get you back in here, all right? Okay, so choose a body. Okay, I'll choose the elevator. What are all the forces on the elevator? There's a tension in the string up, in the cable up, capital T. There is the elevator's own weight, capital mg. And are there any other forces on the elevator? Well, is there anything else touching the elevator? And the answer is yes, you're touching the elevator. Okay. And so you must exert a force on the elevator. Now, this is where I want to emphasize the mistake that so many students make with this kind of problem. I say, what other forces on the elevator are there? And most students, just learning this stuff, will say, the weight of the man is a force on the elevator. And that would be dead wrong. The weight of the man is a force on the man. It is not a force on the elevator. Nevertheless, the man does exert a force on the elevator. I'm going to call that force F. Okay. Now, if this were a Newton's first law problem, if the elevator were not accelerating, and you said that the weight of the man is a force on the elevator, you would get the right answer for the tension in the cable. But you will have done the problem incorrectly. If, in this case, where the acceleration is not zero, you say that the weight of the man is a force on the elevator, you'll get this problem wrong. Okay? So at any rate, we have chosen plus y up. The forces are all self-resolved because it's a one-dimensional problem. So the sum of the forces in the y direction has to be equal to the mass of the body, which is capital M, times the acceleration of the body, which is a, and that is equal to T minus F minus mg. So I will point out, we now have, assuming that a is not an unknown, in this particular situation, what I want to find out what the tension in the string is as a function of a. But I also have another unknown here that I want to find out. I want to find out what is the force that you exert on the elevator as a function of a. So what I have is one equation with two unknowns. And again, the two unknowns are t and f. And so I'm not done with the problem. I have to choose another body. Okay, so the other body that I will choose will be u. Okay, so here's u. And we say, what are all the forces on you? Well, there is your own weight. That's little m times g. Okay. And is there anything else exerting forces on you? Yes, the floor exerts a force on you. And what do we normally call that? We usually call that the normal force. So that's what I'll call it here too. And that's all. Okay. So there's a normal force and a weight. Those are not going to be equal because you, like the elevator, are accelerating. Okay, so now we apply Newton's second law. So the sum of the forces in the y direction for you is equal to m times your acceleration. But your acceleration is the same as the elevator's, so I can still use a for that. Okay, and that's equal to n minus your weight, mg. So let's draw a box around that. Now what have we got? Well, alas, now we have two equations with three unknowns because n, t, and f are thought of as unknowns in this problem. But this is the point at which we say, aha, what is the normal force? The normal force is the force that the elevator exerts on you. What is the force, capital F? That's the force that you exert on the elevator. And therefore, because of Newton's third law, we can say that the vector n must be equal to minus the vector f. Okay. That is to say, the magnitude of n has to be equal to the magnitude of f. Okay. And so I can rewrite this equation as ma equals f minus mg. Now I can solve this equation for f. F turns out to be, well, let's do that. So f is equal to m times g plus a. Okay, let's get a little more page here. And so now I can take that and put it into this equation up here, and so I get ma is equal to t minus f, which is mg plus a, minus mg. If you now solve this, you'll get what we already know is the correct answer from the case where we chose everything as the body. We get m plus m times g plus a. Let's take this one step further. Let's go back and find out what n is. Okay, n is equal to, from this equation back here, m times g plus a. Okay. And let's ask what n is. N is how hard you feel the floor pushing up on you. In other words, it's how heavy you feel. So think about your experience riding in elevators for a minute. What happens when you're on the ground floor and you push the button to go to the third floor? If you think about it, as that elevator accelerates away, going up. It has a positive acceleration, and you feel heavier. In other words, n gets bigger because a is positive, and so what you feel is you feel the floor pushing up on you with a force bigger than your own weight. And essentially that means that you feel heavier. Similarly, when you are coming up on that third floor and start slowing down, all of a sudden you feel lighter because you feel the floor pushing up on you less hard. It's actually much more complicated than that. If you think about it, you have sort of a funny feeling in your stomach when you're either speeding up or slowing down. That's because you're used to your muscles having to hold up your stomach with a certain force, and so you're not aware of that. But if that gets bigger, you suddenly feel heavier. If that gets less, you suddenly feel lighter. Okay, so that's the elevator problem, and that's, I guess, the end of this video. Well, you can stop the video if you like. I'm trying to get my mouse to work here. My mouse seems to turn off, so